On. Okay. Thanks. Okay, welcome everyone to the fourth day of the workshop. As our first talk, Gary will tell us about K-sum and geometric breadth. Yeah.
Thanks for the introduction. And this is joint work with my advisor, Marvin Kuhlmann. And let's just start. So I'll start with the K-sum problem. And I'll go over it quickly. We are given K sets of integers of size at most n, and we want to choose K elements out of these K sets such that they sum up to a value P. And there's a simple meet in the middle algorithm to do this in n to the K half rounded of 5. Probably all know. And especially the case where K equals 3 has been a barrier since Gajentan and Obermaß in 95. And the three-sum hypothesis says that we can not solve this in time of n to 2 minus epsilon. And in general, the K-sum hypothesis states that we cannot solve this problem in n to the K half rounded up minus epsilon. Okay, and our research question with K-sum is the following. What is the most general class of problems which is captured by the K-sum or the three-sum problem? And the research question is a bit vague, so you immediately get some questions yourself. So how do you find the class of problems? And the way we do this is we are inspired by descriptive complexity theory. We construct a class of logical problems and see how they connect K-sum and Q-sum. This has been done before for the orthogonal vectors problem, like Gao et al. And what does it mean to be captured by the K-sum problem? This just we will define this in the notion of finite incompleteness. Okay, let's try to build this class of problems. And we'll build this by making up some examples we would like to have inside. So, of course, we would like to have a three-sum problem inside this class. And maybe a variant of the three-sum problem, which is called the average problem. So you want to see if A plus B half is equal to C. A variant of threesum where we ask if every A and A is if every A and A is part of a threesum triplet. Vector threesum problems where the elements are no vectors, and you ask does the equality hold for each dimension. This problem called additive sum-set approximation, which seems a bit different for now from the rest. We want to ask is A plus B a subset of C plus a set 0 up to T? And this is actually similar to these above because this would just translate to for all A and A, for all B and B, there exists a C such that A plus B is between C and C plus B. And some kind of database queries where we ask, database queries with additive flavor where we ask whether there exist 3 people with average age 20 and a cumulative wealth more than 1 million. Okay, so what do these problems have in common? So we first have some quantifiers, which could be existential or all quantifiers. And inside you have a linear arithmetic formula over the entries in the vectors and possibly some free variables. Okay, and given such a formula phi, we can now define a model checking problem, which we call the first order properties over the integers phi, whereas input we are given the sets A1 up to AK and the free variables T, and we want to ask this phi hold for the sets A1 up to AK and instantiated free variable. And now we just union over all possible phi's and create a class of model checking problems. And we differentiate now by quantifier structure. We said in the following we will say FOPZ exists. It's just where the model checking problems where all quantifiers are existential. Okay, without loss generality, you can assume that the quantifier P part is of the following form. So it's a disjunctive normal form. And for each vector aj, you have some coefficient vector, which you multiply with. And then you ask if it some certain inequality holds with a constant thi after replacing the variable. This is a routine in integer linear arithmetic. So in DNF, you can turn just like in propositional logic, and you can assume inequality by turning two equalities into two inequalities and stuff like this.
And sorry, what's the definition of linear arithmetic formula?
So assume integer programming, anything you can write in integer programming.
So then you say that every formula expressed in this arithmetic type can be expressed in this form. Yeah?
Yes. Okay, now let's introduce fine-grained completeness. So a bit of notation, we will write A is less than or equal to K to B if there's a fine-grained reduction from A to B. And we have the following definition of completeness. We have a problem C, which is solvable in time Tc of n, and a class of problems calligraphic C, which are all solvable in time T calligraphic C of n. And C is fine-grained complete for the class calligraphic C if C is a member of this class. And if C is solvable in time Tc of n1 to the minus epsilon, then all problems in this class of problems are solvable in time Tc, T calligraphic C, and to the 1 minus epsilon. Right. So the intuition is just if you can speed up the problem C, you can speed up everything in this class. And why do we look at this? So first, the obvious thing is the algorithmic consequence. We have a faster problem for C, we get faster problem for everything. But also the other way around, it seems unlikely that the problem C has a fast algorithm, because then so would all the other problems. Okay, let's start with the existential fragment. And the case of, and we have a theorem that says that the case-sum problem will be complete for the class of problems that FOPZ exists with K quantifiers, with K existential quantifiers. What does that mean? It means that we can turn this ugly thing into a case-sum formula. And how would we do this? So also notice that the vectors can have different dimensionalities. And the first thing to do would be to try to remove the disjunction. This you can do easily by just using commutativity of existential quantifiers and the disjunction. So you can get rid of the disjunction. And then you are left with some conjunction of inequalities. And I'll just show you how to remove one inequality. So there's this trick by Virginia and Ryan Williams, which says that let's define pre L of x to be the number formed by the L most significant bits of x. And it holds that the sum of A1 up to AK is bigger than Z. If there is an L and B such that if you take the sum of the numbers formed by the L most significant bits of A1 up to AK, then you are equal to the number formed by the L most significant bit of C up to some constant B. So you probably already know this from the reduction from negative triangle to exact triangle. And what this just basically means is you can get rid of inequality by the cost of a logarithmic factor. Okay. So what this theorem says that any problem in this class reduces to K-sum, and this is particularly interesting for hard problems, because then we get lower bounds for K-sum. And a simple example would be that we can write the 3 uniform 4 hypercube as an FOPZ exists formula with 4 quantifiers. And we're also able to lift this theorem for odd K, so an odd number of quantifiers to counting. So counting the number of solutions to an FOPZ formula responds to counting the number of solutions to K-sum. And for this, we needed to show an equivalence between K-sum and sets and multisets. And the reason is a bit subtle. So if you try to use this key ingredient, this lemma, then the number formed by most significant bits of two different numbers can be the same. So if you take the prefix of the numbers, you can have the same number. And if you, for the decision case, you don't care. But if you want to count, you need to keep track how many times you have this. Interestingly, we were only able to show this for odd k. Maybe we can show this for odd k. And more interestingly is recently, it has been shown that counting the number of threesome solutions is equivalent to threesome. So we can actually make use of this and say that counting solutions to FOPZ formulas with three quantifiers reduces to threesome also. And this has been shown as in a randomized version in 2023 and has been de-randomized recently. And we will crucially make use of this later on. So can we somehow now connect threesome with other quantifier structures? So with the existential case we're done, but can we somehow reach out to other quantifier structures? And yes, we can. And I'll give you a quantifier change, a simple quantifier change from threesome to this additive approximation problem. Firstly, why is this a quantifier change? Because, okay, from the three existential quantifiers, you go to these quantifiers. And to do this, we start with a bit more structured version of threesome, with convolution threesome. So we are given three arrays, A, B, C. And we want to ask, do there exist three indices, such that AI plus BJ is equal to CK, and the indices add up to the same thing? That's okay. So the indices of I plus J equals to K. And we perform the step, the usual step from the reduction from convolution threesome to threesome. So we multiply each index with 100m, where m is a big number, and add up to it the value AI. Okay. So what happens is now that if we have a threesome solution in the sets A prime, B prime, C prime, then we also have a solution to convolution threesome. And this basically happens because the value m is so large that you can only balance it if the indices measure. And how will this look like? It will look like the following, that all points will be very clustered. So they will be clustered around 100m, 200m, 300m, and so on. And let's have a look at it locally, a bit more locally. So if a point lands in the cluster 100 IM, then all the points which land in this cluster will even land between CI plus 100 IM minus 2m and plus 2m, because m is so large. And what we can do, yes, so we at the cluster 100 IM, we have no threesome triple if all A prime plus B prime land in this red area. And we would now like to just, so let's create these helping points, which suggest the start of the red area and the point just to the right of the of C prime. Then we can cover this. Then we know there is no threesome triple in this cluster if all points lie between these two segments with the addition of the factor m to m. Yeah, so it's a very simple quantifier change, and the main difficulty is to start with the red problem with convolution threesome. Okay, so now I'll just tell you about other complete problems for other quantifier structures, but this time without a proof. I want to tell you about the Pareto sum computation problem. So you are given two sets of d-dimensional integers of size n, and you want to compute the non-dominated vectors of A plus B. And the vector is dominated by the usual definition of domination. A vector V dominates a vector U if this holds in all indices. No. And I'll just show you a picture. So you have the set A, like in 2 dimensions, you have the set A and the set B. You compute the sum set, and now you look at the non-dominated vectors of the sum set, and you take, so the non-dominated vectors in this will just consist of the orange points. Similarly, you can say you want to satisfy these FOPZ formulas, such as dominance, so every A plus B should be dominated by some vector C. Every vector C should be of the type A plus B, and there are no distinct vectors C, C prime, where one dominates the other. This is equivalent to this formulation. And sadly, this is not a decision problem, so it's not an FOPZ. But it turns out that this is equivalent to its verification version, where you are given a vector, a set C, and you want to check these 3 properties. But even simpler, we can show that only checking the first property suffices. And we get that this problem, just checking the dominance, is complete for the class rho PZ for all 4 liquids. And the second complete problem I want to talk about is a variant of the Hausdorff distance. So let's start with the Hausdorff distance under the L infinity metric. So you're given 2 sets, BC, and you want to find the largest distance from a point B to the nearest point C under the L infinity metric. There's a slight problem with this distance, is that you can have the 2 same sets, but just translate it, and you get a positive distance, but maybe you don't want this. So people have looked at the Hausdorff distance under translation, where you're also now able to translate the vectors in C. And the decision version just asks, is this smaller than some epsilon? And we now look at the following problem, the Hausdorff distance under M translation. So instead of looking at all possible translations, we just look at a candidate set of translations, and we want to find the Hausdorff distance under translation for these candidates. So this makes sense in the context of approximation algorithms, because you get an upper bound if you plug in some candidate set. And if we now say that the set A has to have exactly n vectors, then we get a complete problem for the class FOPZ exists for all exists. Okay. Yeah.
Is the fact you're using directed non-Hausdorff distance matter? Okay. They're starting the definition is like that's not normal Hausdorff, but yeah, that's interesting. Okay.
So let's just have a bird's eye view on all the things. So we have here all 3 quantifier classes, and in orange you have this the complete problem, and you can always land in one of these quantifier classes by just negating your formula. And we have also some quantifier changes. So we can reduce all formulas from for all exists to 3-sum. This I didn't show you. It's a bit more involved. And you can also go from 3-sum to this additive approximation problem, which is member of this class, the FOPZ for all exists. And what this basically means is that every FOPZ formula with 3 quantifiers either reduces to this Hausdorff under n translations problem or the Pareto sum verification problem. And furthermore, if you use now the argument that you brute force the first k minus 3 quantifiers, and the rest you reduce to either one of these 2 problems, then you can actually solve every FOPZ formula faster, if and only if you can solve the Hausdorff distance under n translations and Pareto sum verification problem faster. So you get 2 complete problems. So we would like to have one, but we couldn't manage, so we have 2 complete problems. So this picture also leaves some desire. So can we somehow go back to 3-sum? And the answer is yes, but only for a special case. So let's say, I'll give you a definition. Linear integer arithmetic formula phi has inequality dimension 3 if you can rewrite it using at most 3 atoms or 3 inequalities. So you have like, this is an inequality, and you have 3 3 of those. And the theorem we show is that threesome is complete for problems with 3 quantifiers if the inequality dimension is at most 3. So if the inequality dimension is at most 3, you don't care how the quantifier structure looks like, you can directly reduce to threesome. And I'll just show you a proof sketch for the case where we have true for all quantifiers and an existential quantifier. So assume we have some kind of wishful disjointness property that for all vectors A, B, there is at most one C which fulfills this formula. This is a strong property, but if we have this, then we know that all AB, if the formula is satisfied, then all AB need to have at least one, and at most one, so they have exactly one C which corresponds to this, which fulfills the formula. So then, by a simple counting argument, you just say that the formula phi is true if you have exactly number of A times number of B, size of A times size of B many witnesses. If you have this very strong property. And for this, we can just use the counting results because we now just need to count the number of witnesses. So now we would like to obtain this disjointness property. And for this, we firstly massage a bit the sets A, B, and C. So you look at the inequalities that are given here, and you multiply, you create a vector of size 3 where you take the coefficient of each inequality. So A1, A, alpha 2A, alpha 3A, and so on. So in each dimension, this basically will correspond to the inequality above. And if you assume now that phi is in F, then each co-clause can look like the following. So you want, for example, the first inequality to be satisfied. Then you say that in the first dimension, A prime plus B prime should be dominated by C prime. And this will just correspond to satisfying first inequality here above. If you want to take the negation of the second inequality, you will just say, okay, in the second dimension, A prime plus B prime is bigger than C prime, greater than or equal to C prime plus 1, and so on. So this is how a co-clause would look like. And so now we just reduce this to a geometrical problem. So assume you're given now a fixed C prime, then so here, assume your C prime is fixed, then the solution space of A prime plus B prime will now correspond to an orthant in 3-dimensional space. Because you have an intersection of at most 3 half spaces. And this is for one co-clause. And now we take the disjunction of many co-clauses. This will just be a union over these orthants. And now we do this for every C prime. And we get a lot of orthants which are possibly overlapping. And now what we do is we make these orthants disjoint by creating boxes R1 up to Rk, which enclose the union of all these orthants, and these are disjoint. And now it's just now it just remains, so now we have this disjointness property, and it now just remains to count for each box the number of A plus B's that lie inside this box. So this is just a high level idea. And you can now show a simple application of this theorem is that we can now just immediately get the reduction backwards from the additive approximation problem to threesome. And the proof is basically just this. So it has 2 inequalities, and you can directly reduce it now to threesome. There's an application of the theorem. Okay, so together with this, we have the following view of all the things. In red, you have some inequality. There are the problems which have inequality dimension 3. So they reduce back to threesome. And I also put some examples here. Yeah. So as I said before, we would like to have one complete problem. So we would really like to know if there's a reduction from Hausdorff under n translation to Pareto sum verification, because then we would end up with one complete problem, but we gave this to many people and it seems to be a very difficult problem. But we still have some open questions, so we would like to know if k-sum is equivalent, fine-grained equivalent to multi-set k-sum for all k. We were only able to show this for odd k, and this seems to be doable, it's an open question. And there's some other questions we see more difficult. We would like to know if the class f of z for all exists is actually in subquadratic time. So is this class of problems here easy? And the way to start with this would be to start with a simpler problem. Is the following version of p-sum in subquadratic time? Okay, thank you.
This is all for real? No. Like it's only integers?
Only integers. So yes, you're right. This is only integers, and it's a good question. I'm sorry, I have to go wait back. Yes, here. It's because this bit trick here works on the integers. We would like to know some equivalent on real numbers. We don't know. This would be super interesting. If you can do this, then you probably can do everything. So we don't know what to do.
So does it subsume all these reactions for QLDT by target?
No. The LDT things are different. So the LDT things, they look the other way around. So we reduce the pre-sum, but they
lag in one of those four boxes, right?
Yes, of course. But we don't show hardness of these things. We show easiness. We show pre-sum easiness. In the LDT paper, they show the hardness.
Oh.
It's a different thing. But yes, the LDTs are inside this, but even more than the LDTs.
Let's thank Kara again.